So this is lecture number 2 of the numerical series. So we have covered some numericals in lecture number 1. उसमें हमने utility functions की shapes and drawings करी थी and we found the MRS in that lecture. Now carrying forward from that, we in this lecture we are discussing one of the major questions that is asked in the exams, that is you have to tell whether the utility functions given to you are convex or not. So just to revise, in lecture number 1, when we had to basically show what is the curvature of the curve, whether the utility function is convex or not, what we did was हमने MRS निकाल लिया था. So suppose this was your MRS, y upon x. So what we saw was, if x was rising, is my MRS falling or not? Then if MRS is falling, my ICs were convex to the origin. एंड ये मेथड हमने सिर्फ तब फॉलो करा था जब बोथ एक्स और वाई जो हमारे थे वो गुड कमोडिटीज थे. जब हमारा एक भी कमोडिटी, फॉर एग्जांपल हमने एक क्वेश्चन किया जिसमें एक हमारा वाई बैड था, एक्स गुड था. सो इन दैट क्वेश्चन व्हाट वी डिड वाज वी फाउंड द second derivative to guess the curvature. If second derivative turned out to be positive, we said that the utility function was convex to the origin, otherwise concave. So this was the method used. But now we move on to the second method. Basically, हर बार ये MRS से IC's convexity बताना is not easy. So now what we do is we have a mathematical method where we can guess the convexity of the ICs by a very simple equation. So you just put your values in an equation and you know whether ICs are convex or not. Because this is an intuitive method, it might not work in some utility function. For example, अगर हमारा MRS आ जाता है this, something like this. So now it becomes very difficult to solve by this simple method. It is very easy for simple utility functions, but for some complex utility functions, this method becomes difficult. So now what we do is, next is we have a mathematical equation to know whether ICs are convex or not. See, there are two methods now. One, एक तो ये जो इंट्यूटिव वाला मेथड था, अब न्यूमेरिकली भी देयर आर टू मेथड्स एंड बोथ मेथड्स आर एग्जैक्टली ऑलमोस्ट द सेम. सी फर्स्ट मेथड इज, जब हमने पूरा एनालिसिस करा, द फर्स्ट थिंग दैट वी डू इज वी फाइंड द MRS and we differentiate MRS with respect to x, right? When you differentiate MRS with respect to x, basically you are saying कि अगर मैं x बढ़ा रहा हूँ, so how is my MRS changing? This is the meaning of this derivative in star. Now, if x बढ़ाने से my MRS is falling, right? Then I say my ICs are convex to the origin, similar to the thing that diminishing MRS, or you can say convex ICs, right? Both things are similar. So this is one method. The other method is when we use the bordered Hessian. If this condition is satisfied, this condition that you can see, if this is negative, then we say that the ICs are convex. And in this case, we say that utility functions are quasi-concave. So this is also a condition for convexity. So star and double star are two conditions that we use to guess whether MRS is diminishing and ICs are convex to the origin. अगर हम दोनों conditions को closely देखें तो the denominator is same. The only thing that is different is uy, right? In ये वाले term में ये है. So now the thing is, the conditions will not differ when both x and y are goods. But then when y, if suppose your y is a bad commodity, then the conditions would differ. And in that case, if one of the commodity is a bad, you should use this condition. So you would use this condition only when x and y are good. ये जो फर्स्ट चार वाली कंडीशन है, इट इज वेरी मच सिमिलर टू योर सेकंड डेरिवेटिव. ठीक है, जब हमारा सेकंड डेरिवेटिव जो होता है वो पॉजिटिव होता है तो हम बोलते हैं आईसीज आर कॉन्वेक्स. बट इन दिस केस MRS हम नेगेटिव क्यों देख रहे हैं? क्योंकि MRS इज द नेगेटिव ऑफ योर स्लोप, राइट? सो नाउ द थिंग इज, if your x and y both are good, you will refer to this condition, double star. But if any one of the commodity is a bad, right? So then you refer to this condition, or you can also refer to one. So you can also find the second derivative that we did in lecture number 1. So lecture number 1 में there is a question when y is a bad and we have use this condition. So kindly check. In this lecture, I will not use this condition. I will use this condition because it is simpler. अगर ये satisfy हो रही है और दोनों commodities goods हैं, so ICs are convex to the origin. I don't need to use this condition. और जहां पर एक bad है तो उसके लिए मैंने lecture number 1 में I have already solved a question. So for this lecture, I won't solve this condition. This has already been done in lecture number 1 numerical series. So now let's start curvature. इसका जो इंट्यूशन है ये कंडीशन कहाँ से आ रही है? दिस इज योर बॉर्डर्ड हेशियन. आई विल डिस्कस द इंट्यूशन ऑफ दिस टुवर्ड्स द एंड ऑफ दिस लेक्चर, बट फर्स्ट लेट्स डू द क्वेश्चन प्रैक्टिस पार्ट. Now, this is the Cobb-Douglas utility function that we have, uxa. Now, what you have to do is first you have to find the first derivative, second derivative, x, 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 x. इसमें x और y दोनों good commodities है, so we won't confuse it. फिर यहाँ पर आता है. Now, let's write the condition from double star. u x x u y का square u y y u x का square. So there is a typo in Snyder. They write ये uy की जगह उन्होंने ux लिख दिया, but it should be uy. So it's just a typo. You can correct that. Don't get confused. Although it would not change anything for the signs, right? So now, if this is the case, so uxx. So this is multiplied by uy का square. So you see यहाँ पर हम assume करते हैं a की value is less than 1 and b की value is less than 1. If a's value is less than 1, this portion would be positive, this would be negative. यहाँ पर a minus 1 है, right? So this would be positive, this would be negative, and this would be positive. Now, uxx is negative. यहाँ पर हमने just पता लगाया uy here is positive. और प्लस uy का स्क्वायर है तो एनी डे पॉजिटिव होगा. ये माइनस है, ये इसके अंदर वाली टर्म इज, बोथ टर्म्स आर पॉजिटिव. प्लस uyy अगेन इज अ नेगेटिव टर्म, राइट? और इसके बाद वाली टर्म इज अ पॉजिटिव टर्म. तो अगर हम ओवरऑल देखें, यहाँ पर नेगेटिव पॉजिटिव क्या हो जाता है? हमारा नेगेटिव हो जाता है. और यहाँ पर नेगेटिव पॉजिटिव क्या हो जाता है? लेट मी यूज अ रेड वन. अगेन नेगेटिव, और यहाँ नेगेटिव, अगेन नेगेटिव. सो व्हाट वी सी इज 3 नेगेटिव टर्म्स इकट्ठे आएंगी एंड दिस वुड बॉयल डाउन टू लेस देन 0. सो this is something that I'm doing intuitively. You can also solve, you can take the values and solve. You will see that this is coming out to be less than 0. So that means these kind of functions are convex to the origin, and also we can say that the utility function is quasi concave, right? So this is the first example. Let's move on to the second example. Let's take an example of a perfect substitutes. Okay, so the first job is to finding f1. I'll solve this with you simultaneously. So now f1 की वैल्यू a हो जाएगी ग्रेटर देन 0, f2 की वैल्यू b हो जाएगी अगेन ग्रेटर देन 0, f11 की वैल्यू 0 होगी, f22 की वैल्यू 0 होगी, f12 की वैल्यू 0 होगी. In this, now let's use the condition uxx uy का square minus 2uxy ux uy plus 2 not 2 uyy का square uy का uy नहीं ux का square, and this would not be right. So this should be less than 0. So uxx क्या है हमारा यहाँ पर? 0. uy कुछ भी हो मैटर नहीं करता. I'll write as it is minus 2. uxy क्या है? This is coming out to be 0. ठीक है. ux is f1 only. f2 बोले या uy बोले एक ही बात है. ये हमारा b है. ये अगर हम करेंगे तो यहाँ पर u y y 0 आ जाएगा. सो दिस होल टर्म इज कमिंग आउट टू बी 0. अब जब हमने ये कंडीशन देखी तो हमने एक स्ट्रिक्ट कन्वेक्सिटी की कंडीशन देखी है. जब ये जीरो पे सेटिस्फाई होती है, वी से दैट योर यूटिलिटी फंक्शन इज quasi concave, but the ICs are not strictly convex, they are just convex straight and they are straight lines. तो जब ये जीरो आ रहा है तो यानी ICs would be drawn as straight line, but that does not mean that ICs are not convex, they are also called convex. And I am clearing the terminology once. यहाँ पर ये जो यू एक्स एक्स है, यू एक्स एक्स का मतलब है इस फंक्शन का डबल डेरिवेटिव विद रिस्पेक्ट टू एक्स. यू वाई वाई है, उसका मतलब डबल डेरिवेटिव विद रिस्पेक्ट टू वाई. यू एक्स मीन सिंगल डेरिवेटिव, यू एक्स वाई मीन्स क्रॉस डेरिवेटिव. और अगर मैंने उसके जगह यहाँ पर एफ वन का मतलब इज नथिंग बट यू एक्स ओनली. दिस इज यू वाई ओनली, दिस इज यू एक्स एक्स, दिस इज यू एक्स वाई एंड this is u y y. Right? So these are the terminologies that I will be using interchangeably. Now let's move on to the third example. What kind of utility function can we take? We can take this kind of a utility function. Let's solve for this. Now ux, let's be consistent with the terminologies. ux क्या होगा? इसका double derivative. uyy is again 2. And then you have the condition. Uxy is left. So if you differentiate this with respect to y, you will get a 0. अब condition क्या है? बार बार condition लिख रहे हैं so that we learn it. So uxx would be 2, uy का square would any day be positive, 2y का whole square minus 2 into 0 plus this would be 2 and ux का square. So you see this turns out to be 0, and if you sum this and this would be nothing but 8y square plus 8x square. Any day positive. So is it satisfying the condition of quasi-concavity? Check. It is not less than 0 as per the condition. So that means in this case, ICs are concave and not convex. So is the utility function quasi-concave? No. I'll explain quasi-concavity in a while. Now let's move on to another example. Let's take this example as, let me check some of the past years. What more we have? Just a minute. Okay, so this is one of the past years. Now here, let's solve for ux. इसमें cases बनेंगे. Treating y as a constant, you would have -1. So this would get y upon 100 minus x का whole square, ux square. uy की अगर हम बात करें, so this would get 1 upon 100 minus x. Now this is can be positive or negative depending on the values of x. So in this case, if x is less than 100, so this uy is positive. If x is greater than 100, this uy would be negative. So you'll make cases under this. And this would always be positive, ux. So let's move forward. uxx. Let's differentiate ux with respect to x. Now again, there are going to be cases. Case number 1, अगर तुम्हारा जो x है उसकी वैल्यू लेस देन 100 है, then uxx is negative. Case 2, अगर तुम्हारा x की वैल्यू greater than 100 है, so then uxx becomes positive. माइनस और नीचे वाला माइनस कैंसिल हो जाएगा and these are the cases. Now let's find uyy. You have to differentiate with respect to y. This is will come out to be 0. Okay. Now let's find uxy. We have this. Let's differentiate uy with respect to x. This is coming out to be positive in any of the case क्योंकि denominator में हमारा square है. Now let's write the condition on a new page and then let's solve. You have uxx uy का whole square. ये पहली term है. So let's individually solve this term. Now इसमें भी you have cases. So let's do one thing. Let's solve the full condition for cases. Case 1 ले लेते हैं. X is less than 100. If this is the case, then let's see what happens to the condition. Condition लिख लेते हैं. This has to be less than 0. Now let's see if it is holding true or not. Uxx is negative. Uy का square, see, this is uy, right? Obviously there are cases, but we know that इसका square है, so it is always going to be positive. Minus 2 into uxy. See, uxy is always positive. So 2 into some positive quantity. ux की अगर मैं बात करूं तो ux is always positive. uy की बात करूं तो uy में conditions बन रही हैं. x अगर less than 0 है तो uy positive है. uyy की बात करें तो that is coming out to be 0. And ux के whole square की बात करें, it will always be positive. So it doesn't matter because uyy is coming out to be 0. So now if you see, this whole term would get negative and this whole term will get negative. So that means this condition would be satisfied if x is less than 100. Then your utility functions are quasi-concave. But the only caveat is that I can use this condition only when both n x and y are goods. So are they goods? See, they are goods when this condition is holding true, right? Your good y turns out to be a bad when x is greater than 100. So under case 1, everything is fine. This function is, this IC is downward sloping as well क्योंकि तुम्हारा MUX और MUY भी positive है, downward sloping convex ICs, right? So if you go about drawing them, this is your y, and if x is less than this, so is it a limiting case? Meaning x को अगर मैं 100 रखूं तो what will happen to the 100? Then utility won't be defined. So then that means 99, then it would be fine. Okay. So this is for case number 1. What happens for case number 2? First thing is that IC's the utility is not defined for this thing. So now after x is equal to 100, the utility function starts sloping upward. But the curvature, for the curvature, you will have to check your, that we did in lecture number 1. So as a homework, you can do that, or otherwise I'll guide you once how to go about it. Curvature would change, of course, with cos cube y. Yes, curvature would change. So this is, So as you know, for x greater than 100, you cannot use this condition. You will either use जो starting में condition हमने दी थी DMRS upon dx. And don't forget, when you are putting values in this, तो x greater than 100 की values अलग हैं. So you put them. So what I feel is, if you solve it, it would be less than 0 only. So most likely you'll get a curve like this. Whether it would get 0 or wo, I'm not concerned about the scaling. I'm just telling you the shapes of the curves. But solve it, and in the comment section you can basically we can discuss what would be the shape after this. So most likely it would be also convex. ये diminishing आ जाएगा हमारा MRS, but you can't use this condition, the same condition for this, because one good becomes a bad after this. So this was this question. Now let's move to another question. Now again here x and y both are good commodities. So you can say we can safely use our quasi concavity condition. We can safely use, and you will see that this would be satisfied for this as well. So they would be downward sloping convex to the origin ICs as well, because this condition would be satisfied. So now after this was the basic numericals. Obviously, we will dig deeper and do more of them. But for the time being, let's understand ये quasi concavity की condition बोल क्या रही है. What is the intuition? See, now what happens in your utility space, that utility function is actually a function in three variables, x1, x2, and u. Now your utility is also changing, but when I draw ICs, I assume कि हमारी utility same है. But when you draw this function, it should ideally be drawn in a 3D space where u is also changing, x1 is also changing, and x2 is also changing. But now when you draw this utility function, it becomes a 2D graph. And now when you are drawing ICs, these are nothing but these are the level curves. Level curves mane when you assume u to be constant and only two variables x1 and x2 are changing and utility is constant, these are known as level curves. So when you plot these level curves, for example, for any utility function, this is my level curve, meaning assuming u to be constant, and now it is in a 2D graph. So now if you mark the upper contour set, all the bundles which are weakly preferred over these bundles. To understand all of this, you need the theory lectures. For the link for that is in the description box. So this is the curve, and this is the upper counter set, or you say weakly preferred set. Now in this set, what was told to you is that now you take any two extremes and take one average. Now if this average point lies in the upper contour set, we say that ICs are convex, right? And when these ICs are convex, when this condition on level curves is satisfied, we say that the U is a quasi-concave function. This is purely maths, and we are just using an application of that. So U क्योंकि quasi-concave function है, उसकी वजह से जो उसके level curves हैं, वो क्या है? ICs. उनकी shape क्या हो जाती है? Convex हो जाती है. और इसका मतलब ये भी है कि लेवल कर्व्स जो यहाँ पर ड्रॉ है, अगर मैं वीकली प्रेफर्ड सेट बनाऊं यहाँ पर, तो ये सेट में अगर मैंने एक्सट्रीम्स को ज्वाइन करा और मेरा जो एवरेज है, अगर ये अपर काउंटोर सेट में कहते हैं, तो आई ऑल्सो कॉल दिस शेडेड रीजन एज अ कॉन्वेक्स सेट. दिस इज माई कॉन्वेक्स सेट मैथमेटिकली. Now, if all this is happening, U is quasi-concave, there is a mathematical condition which is derived using bordered Hessian, which is this is a condition that says U is quasi-concave function, and its level curves, basically ICs, would be shaped convex. And these IC that are shaped convex is on the assumption that averages are preferred over extremes. Why? Because when you drew the convex set, इसमें जब हमने upper contour set draw करा, तो what we saw was that your average was lying on the in the upper contour set. That is why we call this a convex set. This is all maths. So that is why ICs are convex to the origin. Now, I want to repeat the same exercise when Y is a bad. Okay, your X is a good commodity and your Y is a bad good. Now, I know that in such situations, suppose the shape of my ICs is like this. So it is upward sloping. And now the thing is, if I mark the upper contour set under this, so what would be the region? See, Y is a bad. So utility increases in this region. So if this is a level curve, this is an IC, and if I have to plot the level curve for this upper contour set, this would be like this, right? So in this case, if you join any 2 points and take an average, obviously average is preferred over your extremes in this case. So अगर average is preferred over extreme और ये जो upper contour set हमारा आ रहा है, this contains the extreme value, obviously we call that the function is quasi concave. But when you look into the drawing of it geometrically, is it a convex function? When you look into the second derivative of this function, is it a convex function? No, the second derivative of this function would be negative. So here is where the conditions mismatch. Why? Because quasi concavity simply means कि जब हमने upper contour set लेंगे और उससे हम एक average निकालेंगे, that would be preferred over convex, which is here also satisfied. But geometrically this shapes like a concave. So that is why when one of the commodities, specifically Y, is a bad, the both the conditions differ mathematically. The idea is just because the intuition behind is same, but you can safely use this condition when your X is a good and your Y is a good. And honestly, you can also use this condition when your X is a bad, right? And but don't try using that. If any of the good is a bad, use this condition, second derivative. I just explained the meaning, the why they are coming out to be different. You can ignore this part if you want, because this part is not invariant. But when we do question practice, sometimes it is handy to us. So that was all. We'll do some more question practice in lecture number 3. If you have any doubts in these numericals that we discussed, you can let me know.